Thank you. So I'm going to talk about drones. And you may ask, what's the connection between drones and mobile? And what I'd like to suggest is that there's a convergence between what's going on with smartphone technology and a much bigger movement to bring that technology into the world. Drones are just smartphones with propellers. But because they use many of the same technologies and because they're autonomous, we have the ability to put sensors out there in a way we never have before and created the biggest big data opportunity we've ever seen. So I thought I'd give you a little presentation about sort of the big picture of what we're doing here. This is part of the Internet of Things. This is part of reality capture. This is part of the next generation of big data, and drones are just an example of it. So if you could switch to my slides, please. So in 1972, Apollo took the first picture of the Earth. And for the first time, we were able to see our globe from above. And this changed the way we thought about the environment, about our stewardship of the planet, and about thinking as a planet, not as individual countries. And that was done by satellites. Those pictures were created by satellites. So that was the beginning of the space age, and satellites were the start of what we called remote sensing. Now, what's interesting is that today we're having the same sort of revolution, but it's not in space, it's in the air. Drones are the new satellites. Drones are orders of magnitude cheaper, higher resolution, easier to deploy, dispatchable. This is going to have as much an impact as the original space age did, but it's going to be tied to the internet in the way the space age wasn't. The way to think about this is in a mobile context, is to remember back in 1998. In a conference like this, we would have been having a huge debate about satellite phones versus cell phones. And there was Iridium and Teledesic who were going to put satellites in the air, 64 satellites, and it was going to cover the planet. And then there was this crazy idea that maybe we would just put up like 1 million cell phone towers. And what's interesting is that we now know how this played out. Satellites lost and cell phones won. And it's very interesting to ask yourself, why? How on earth can it make more sense to put 1 million towers on the ground than just 64 satellites in space? And the answer is that cell phones scaled. Those sat phones were about voice. But as cell phones went from voice to data, the demand for high bandwidth, low latency data became overwhelming. The satellites couldn't subdivide the spectrum because of this, far enough to handle the bandwidth. Because of their distance, they couldn't handle low latency. Only cell phone towers could scale to meet the demand. You put the cell phone towers where the demand is, rather than a one-size-fits-all approach of satellites. So think about the same analogy with drones and satellites. And what you see is that basically drones are the cell phones to sat phone satellites. That we now have the ability to reinvent the notion of remote sensing built around internet technologies, built around cell technologies, built around smartphone technologies, and create a bottoms-up revolution to this imagining of the world, this visualization of the world that allow us to manage the planet on a level we never have before. Here's a slide with too much data on it, but basically it just shows you the numbers. It just shows you the economic analysis of drones versus satellites. And the problem is actually just finding a comparable unit. So if you want to survey a farm, for example, for crop analysis, a drone is the only way to do it well, because you can do it every day, you can do it every hour, you can do it 3 centimeters per pixel, and it's incredibly cheap. And if you want to survey the planet, a satellite's the only way to do it. So I just took one level of analysis where the two meet, and that is Kansas, the state of Kansas. If you want to image the state of Kansas every day, it actually costs the same amount from a capital equipment perspective. You take CubeSats, which are very small microsatellites in the air, that cost $1 million each, and you need about 100 of those, a constellation of 100 CubeSats. That's $100 million. Or you can put 200,000 drones on the ground with, charging pads and, autonomous launchers. Not 200,000 people, just 200,000 drones spread around Kansas. And what you would get, and they cost the same amount, both $100 million. But the difference is that the resolution of the drones is 3 centimeters per pixel, and the resolutions of the satellites is 300 centimeters per pixel. The drones get their data in minutes. The drones fly under the clouds, so 2/3 of the planet is covered by clouds at any point in time. And so the drones are under that. They can see it all the time. And the drones are able to scale. You can switch out new sensors. You can do multispectral, infrared, all this sort of stuff. The drones on the ground are able to move with Moore's law, while the satellites have to be launched in space and they're locked into the technology there. Also, the drones are free. The drones themselves, and here's one of ours, the Solo, the drones themselves cost about, right now they cost $1,000, they'll soon be $500. But the marginal cost of the drones is zero. It's a little bit of electricity. Whereas the marginal cost of the satellites is very much not zero. So that's just kind of the analysis. And if you you plot it out, you can actually see the cost curves of drones versus planes versus satellites versus, unoperated drones. So there's 2 kinds of drones. There's those that have operators and those that are fully autonomous. And you see those 4 lines. And what you can see is autonomous drones, in other words, flying robots that just do their thing, are almost unbeatable until you get to 500 hectares area, which is bigger than most farms. So that's a really interesting trend line, because what that tells you is when you take people out of the loop, when you take human pilots and human operators out of the loop and let the robots be robots, let them be autonomous, the cost curves become incredibly compelling. The problem with planes is they have people in them. The problem with operated drones, with pilots, is that they have people. Autonomous drones, like this one here, which just fly on their own, which can be operated as a fleet from 1,000 miles away. One operator can operate thousands of these things. This creates this ability to break the link between man and machine and to scale drones far beyond the human operators. It's kind of like the exact opposite of what Andrew was saying with O2O, where it extends the internet to people. This cuts people out of the loop entirely and just connects sensors to the internet. This is a picture of my grandfather, Fred Hauser. He invented the automatic sprinkler system in the 1930s. And it was very inspirational to me. And so, one of the reasons I kind of got into manufacturing and hardware and inventing and entrepreneurship was inspired by my grandfather. But the fact that he did a sprinkler system also inspires me. And so what I'd like to suggest is that when you think of this drone, don't think of an airplane, think of a sprinkler. A sprinkler is a little sort of dumb robot that sits in your garden or on a farm and just every day does its thing. There's an operator, there's a control panel, and the control panel controls many of these sprinklers, and on a schedule, they come up, they spray, and they come down. What if we could collect data the same way? What if drones could just be populated out there on farms, construction sites, infrastructure, whatever, in little boxes, and that every hour or every day, they'd just pop up, they'd scan the site, and then they'd come back and recharge themselves. And all you'd care about is that every day you'd get this incredibly high-resolution, multispectral imagery of the world. Imagine like Google Street View on an hourly basis from the air, where you have essentially unlimited resolution, multispectral, laser, radar, the works. Imagine if we could measure the physical world as well as we could measure our digital world. Imagine if we could extend the internet out into our planet with things like drones, ground robots, and the Internet of Things. So think sprinklers. And once you think that, then you realize how that scaling is everything. Robots scale in a way that humans don't. So what this means is that we've built a platform that is oriented around the cloud. It's oriented around the internet. Back a few years ago, drones were just flying robots, and you actually piloted them with sticks. And then, of course, all of us who were paying attention realized that people like smartphones. So then drones became robots piloted by smartphones. And then, of course, all of us who were paying attention realized that smartphones are connected to the internet, And so then drones became connected to the cloud. And it is not just a matter of connecting. It's a matter of creating a full stack architecture where code can run arbitrarily on the drone, on the phone, or in the cloud. And this ability to do distributed computational tasks across the whole stack is the way that modern robotics works. It's called cloud robotics. And so what this means is that we have the ability, now that we've got this full stack, we've got these sensors on arbitrary places in the sky connected to the cloud, that we don't even know what drones are anymore. Where they used to be vehicles, then they were cameras, and now they're sensing platforms. We are at, like in the PC world, we're like in 1984. We've just invented the Mac, and we haven't invented like the internet yet. We have suddenly made it possible to put sensors in the sky without any skill required, at low cost, without even necessarily high regulatory hurdles. So now that we can put sensors in the sky and connect them to the internet, the question is, what sensors? What are they looking at? What are we going to do with the data? How are we going to analyze it? How do drones connect to Baidu to deliver the kind of machine learning, deep learning insights that we're already doing with our screens and our fingers, but take that out there to the biggest big data opportunity we've ever seen. These things gather a terabyte of data per hour, and we've just begun. So I wanted to kind of recontextualize this, so to say this is bigger. Now, right now, as we think bigger, as we think about drones as part of the Internet of Things, as part of the cloud, you see it's part of these bigger trends. The big data trend. Reality capture is something that companies like Autodesk are pioneering to take things that begin digital in CAD files and then are built out in analog in the physical world to redigitize them so they can be managed the way digital things are. If we can digitize the planet, we can then manage it like we manage our digital lives, which means the same workflow tools. On the consumer side, these things are used for personal storytelling, this sort of democratization of Hollywood, this extraordinary advances in cameras and video editing technologies and sharing, etc. We're now putting the tools of Hollywood in the hands of regular people. This is part of the broader personal robotics movement. It's part, of course, the broader automation movement. And again, I think it's actually in many ways creating a new space race, but now near space, not distant space. This is the same sort of ability to see the world from above, but now in the hands of everybody, not just the military and big companies. And so I wanted to kind of pull back and show you the broad context of what we have here. I'm going to move back a slide. That slide I just showed you is a Flannery O'Connor book called Everything That Rises Must Converge. And it's kind of my motto. And these are the big trends here. In our world, smartphones and drones are converging. And because we're all starting to use Linux, now we're starting to use the same computer vision algorithms, the same ROS as the robot operating system. There's a huge amount of academic research out there that's been done on Linux, on supercomputers, and now as phones become more like supercomputers, we're able to use all of that research and just stick them right into our platforms. And so by thinking like a phone, like thinking like a connected platform, we're able to tap into these broader development communities, this code that already exists. And so what Andrew's doing with deep learning and what we're doing with drones are on a convergent path. As a matter of fact, we all work together on something called the DRONECODE Foundation in Baidu and 3DR, and also companies like Qualcomm and Intel are all starting to work together to realize that what we thought was separate industries, smartphones and drones and robotics and big data, are all actually becoming one industry. This is actually part of the Linux Foundation. Because we realize that this open innovation approach that Linux pioneered is the way we're going to accelerate the pace of innovation by combining all these interdisciplinary skills and teams into this one big opportunity. So this is what the ecosystem looks like. This is really new. The idea of a distributed computational platform where you have drones, phones, and cloud, and the same code can run in any layer of the stack is the architecture of the future. It's a really hard computer science problem to build these distributed state machines, these sort of really clever messaging systems that allow code running at these different levels of the stack, sometimes out in thousands of feet away in the air, sometimes with non-deterministic wireless connections. But to get that working is essentially like an operating system for the remote sensing system of the future. And I want to show you one last slide, which is just if you look at the trends, the technology trends in the industry, you can see how powerful this is. You have drone, phone, and cloud. The top line is today, where the drone has very low latency. The computation on board the drone is low latency, but it's relatively limited processing power. The phone has more processing power, but a little bit more latency because you're going over a wireless connection. And the cloud has infinite processing power, but longer latency because we've been going from the drone to the phone, through the cell towers, and then into the cloud. But then let's fast forward a year, and now things change. Now, maybe we don't go through the phone to the cloud. Maybe we're using things like OpenLTE, Open Spectrum LTE, to go straight from drone to cloud. Now the drone doesn't have sort of a 1 gigahertz Linux processor, but it runs the exact same Qualcomm stack, the Snapdragon stack, that we're running on the phone. So that's now 3 gigahertz, quad-core, GPU, DSP, the works. Now we start to do things like computer vision, and we can say, well, you know what? We can actually do a huge amount of computer vision on the drone, do whatever we can't do on the drone in the cloud asynchronously at a slower update rate, and then combine the two. Exactly what you just saw with Andrew's demo is something that can be done on the drone. And the point is, the phone may not be necessary. It can be directly just drone to cloud, coordinating between the incredible data and information resources of the cloud, and then the incredible sensing and local processing abilities of the drone. And that's when you start to think about these things being fleets of autonomous vehicles out there measuring the planet. That coordination between the edge and the core, between the drone and the cloud, is what's going to be the next generation of performance and innovation. So basically, this is the lesson. Don't think of these things as toys. Think of them as the Internet of Things. Think of them as flying computation platforms with computer vision and everything else. Think of them as just another stack running Linux and all the software and cameras that work with that. And then this is the kind of stuff we're going to do. This is the future of robotics, and this is the future of drones, and this future is happening right now. You're going to see products from us and others coming out of the next few months that start to do these things that were sort of the holy grail of robotics just a few years ago. Computer vision, sense and warn, sense and avoid, environmental awareness, scene awareness, artificial intelligence pathfinding, machine learning, which Andrew talked about, using the robot operating system to bring in this academic volume of work, LTE connectivity, possibly without using open spectrum, so without the carriers, peer-to-peer swarming, and adaptive learning and fail-safes so that they're safe and can avoid problems. This kind of stuff would have been impossible 5 years ago. It was science fiction 5 years ago. And today, thanks to the cloud and using smartphone technology inside, it's becoming almost trivial. We basically have to wait 6 months, and somebody in our coalition has invented it. You want computer vision, wait 6 months, and it's like built into the Snapdragon stack. You want something like AI, wait 6 months, and it's built into the Baidu stack. And so this ability to converge with these extraordinary technology movements, these industries that are coming together around the sort of the mobile technology stack, allows regular people to do things that were only imagined a few years ago. And to give you a perfect example, 2.5 years ago, I was a magazine editor. And today, I run the biggest drone company in America and one of the biggest in the world. We make more drones every week than all of America's aerospace companies combined. That should not be possible. But the reason it is simply this. Thank you, everybody. Thank you for creating the fastest progression of Moore's Law the world has ever seen, because this creates a bounty that allows people like me to use that technology in new domains to transform them, change the industries, and create new industries that were only imagined a few years ago. Thanks very much.